So in this section, we're going to talk about parameterized curves. So you've already seen parameterized curves um, in Calculus 1 or Calculus 2, wherever those were introduced. But here we're going to see how we can use vectors to represent our parameterized curves. So we're going to move more towards a multivariable calculus view of parameterized curves. So we can actually do some calculus with them and use vectors. So yeah, as I said, we've seen these in calculus class before. For example, we've seen the unit circle is given by um, your x value being cosine of t and y value being sine of t. So just here, we're here like the angle from the x-axis up to. So if I had like a ray going out from here to here, the angle from here, that ray to here would be t. So we've seen that before in calculus class and even in trigonometry class. That's how we saw cosine and sine used. So what we want to do, as I mentioned, is we want to use vectors to parameterize our curves, and this will make doing calculus much easier. So instead of using this parameter, just sticking with this ordered pair for our parameterization, we're going to use what's called a vector valued function. This is a new type of function we haven't encountered before. So we'll end up using more than one variable vector valued functions later in this semester, but for now, let's just stick to a one variable vector valued function. So this is basically a function that you input a number, but rather than outputting a number, you output a vector. So input a number, output a vector. So we can write these as xt and ytj, where xt and yt are just functions of t, just regular functions. So those are just outputting numbers. And then we put them in front of those unit vectors to get us a vector out of that. And so we know that where the vectors are doesn't really matter for a vector, but for us, in this context, we're always going to put our r of t's where they start at the origin. And then what that does is it tells us then the tip of the vector will be at the point xt, yt. And so this gives us a way to think about our vectors kind of tracing out the curves. By the tip of the vector gives you a point on the curve. So for example, here we see if we let r of t be the vector valued function giving the unit circle. So my function here is cosine of t, for x of t is cosine of t and y of t is sine of t. Now let's look at some values here. So if I put in 0 for t, I get cosine of 0I plus sine of 0j. And so that just gives me 1 times I plus 0 times j, which is just I. So r of 0 here is I, and you can see that on the picture here, just pointing in the I direction, and so that gives me the point 1, 0 there on the unit circle. Similarly, we can plug in some other points. So if I plug in pi over 6, then that gives me square root of 2, or square root of 3 over 2i plus 1 half j, and so we can see where that point is on the unit circle. And we could continue with more points. So if we did pi over 4 here, we'd be at square root of 2 over 2i plus square root of 2 over 2j. And so we can see as I change my values of t here, these vectors move along the unit circle and they just trace out the whole unit circle. So as my t goes from 0 to 2 pi here, it will give me the entire unit circle. One thing we're going to see is we can change the parameterization to speed things up or slow things down as well. So we could scale our t so that rather than going from 0 to 2 pi, we'd go all the way around the circle from 0 to 1. Or if we wanted, you could change it to basically be anything you want by scaling the t value there. But for us, for now, we're just worried about seeing that we can actually do this parameterization with vectors. So as you saw in calculus when you did this, parameterizing curves is a bit of an art form. It's not just, you can't just say, oh, here's how you do it. Sometimes it's easy to parameterize a curve. Sometimes it's very difficult. But there is one situation where we always can parameterize a curve quite easily, and that's if you just have a function. So if I have a function y equals f of x, it's always easy to parameterize this. It's not the case that this method I'm going to tell you is always the one you want, but it always will give a parameterization. So if I just set t to be equal to x, then I know my y value is just f of t. So x of t is t, y of t is f of t, and this gives me a parameterization. So whenever you're trying to parameterize the function y equals f of x, this will always work, and it is easy. So that is one case where it works nicely. Now, we're also going to be interested in this course in curves in 3 space. So we need to be able to describe those as well. So it's not so hard to do. We just have a vector valued function, and instead of outputting a vector in 2 space, it outputs a vector in 3 space. Nothing really complicated about it. It is more difficult to graph these things, just like it's more difficult to graph things in general in 3 space, just because it's harder to make. You have to, have depth perception and stuff to get the graphs to work right. So it's a little more difficult. So we'll use a lot of computer graphics to help us for this. So we're going to give just one example here with an animation. So here is the vector valued function cosine ti plus sine tj plus t over 3k. And so notice if I took away the k term, this would just be a circle. But what the k term is doing is it's changing the z value of our vector. So as t gets bigger, the z value gets bigger of this. So you can see it's just basically moving in a circle in terms of the xy directions, but then the vector is getting taller and taller as it goes around this circle, and that's what's giving this spiral curve here in 3 space. And you can see it's easier to visualize this with a computer graphics than it is drawing it yourself, and this is even a pretty simple curve to draw in general. So that's it for our very brief intro to parameterized curves and vector valued functions. Obviously, we're going to spend a lot more time on this. Parameterized curves are going to be very important for our calculus going forward.